Earth's habitable zone lifetime is as long as 7.8 billion years. The total life of Sun is said to be around 9.5 billion years. On the other hand, the estimated life of the universe is around 13.8 billion years. If someone asks you about the almost immortal thing in the universe, what will be your answer? Most of the people will answer that the universe itself will last till the existence of this world, and nothing can survive once this universe has ceased to exist. But this might not be true. The physical world in which we are living is not as simple as we might think. It is much more complicated and mysterious than we might even imagine. Our knowledge about this physical world might not be equal to even a small fraction of what it really is. Black holes are the objects which might even exist when this universe will cease to exist. Before we discuss how it is possible for black holes to be in existence for so long, we might discuss the formation of a black hole. In a few billion years, the Sun will become a red giant, and it will become so large that it will engulf our planet. But the Earth will become uninhabitable much sooner than that. After about a billion years, the Sun will become hot enough to boil our oceans. Our solar system is just over 4.5 billion years old, so the Sun is slightly more than halfway through its probable lifetime. After 8 billion years of burning hydrogen into helium are over, the Sun's life gets a little more interesting. Things change, because the Sun will have run out of hydrogen in its core. All that's left will be the helium. The trouble will be that the Sun's core will not be hot or dense enough to burn helium. Eventually, that force compresses the center of the star to such a degree that it will start burning hydrogen in a small shell around the dead core, which is still full of helium. As soon as the Sun begins to burn more hydrogen, it would be considered a red giant. As the star explodes in a supernova explosion, this produces either a neutron star, or if the star is massive enough, the entire mass of the core collapses into a black hole. If you are looking at a black hole, what you would really notice is the event horizon. Anything that comes out of the event horizon needs to be traveling faster than the speed of light to escape. In other words, it's theoretically impossible. So we just see a black sphere reflecting nothing. But if the event horizon is the black part, what is the rest of the black hole really is? It is the singularity. We're not confirmed what it exactly is. A singularity may be a point when there is no empty space left in the atoms. We know that more than 99.9% of the area of an atom is empty. A wall may look solid, and when you touch it, you feel that there is no empty space in the wall. But if you reduce your size up to the size of an electron, you will notice empty space everywhere in the wall, and you will hardly find anything within an atom. But within a black hole, there will be no empty space, due to singularity. Time becomes slower for an object as it reaches near the event horizon of a black hole, but remember that you will not experience the slowing down of time as you approach the event horizon. But the observer far away from the black hole will see the time slowing down for you. When you will look upon the observer who is far away, you will notice that time has become too fast for the observer. But remember that you are going on one-way traffic. Once you cross the event horizon, you will no longer be visible to the rest of the universe. You may be converted in size less than the size of an atom, although your mass will remain the same. But you will not be alive to experience all these things. Black holes come in different sizes. There are stellar mass black holes, having mass a few times more the mass of the Sun, with the diameter of an asteroid. There are also supermassive black holes, and most of these are found at the center of galaxies. Supermassive black hole at the center of Messier 87 is so huge that astronomers could see it from 55 million light-years away. It's 24 billion miles across and contains the same mass as 6.5 billion suns. As powerful as black holes are, they will eventually evaporate through a process called Hawking radiation. Black holes survive by gobbling down the gas and stars around them, and it's their gluttony that gives them away. They are often surrounded by accretion disks of material they've torn apart and sucked close, like water swirling down a drain. As material draws closer, it begins to travel faster and faster, piling up around the black hole. Friction among the dust generates heat, causing the accretion disk to glow, which outlines the shadow of the black hole, or its event horizon. It wants to hide, but it does a pretty bad job of it sometimes, says Shepard Lehman, a black hole researcher at Harvard University and director of the Event Horizon Telescope, which snapped the first photo of a black hole in 2019. Besides giving a black hole away, the event horizon is also the key to a black hole's death. The material that crosses a black hole's horizon is lost forever, as nothing can escape the grip of these gluttonous monsters. At least, that's what our current understanding of gravity dictates. But this so-called point of no return fails to take quantum mechanics into account. Physicists are still working to develop a unified theory of quantum gravity. In 1974, Stephen Hawking proved that, from a quantum perspective, escape from a black hole is possible, though it is very slow. It takes a shockingly long time for a black hole to shed all of its mass as energy via Hawking radiation. It would take 10 to the power 100 years, or even more, for a supermassive black hole to fully disappear. The entire age of the universe is a fraction of the time it would take, says Priyam Vadanatarajan, a researcher at Yale University, who probes the nature of black holes. As far as we are concerned, it is eternity. It cannot be ruled out that this universe could have emerged from some black hole, and may vanish into the black holes as well.